Hello students, and I want to thank my cousin Cletus Hassellinger for showing me this nice color diagram, one-page proof of the Pythagorean theorem that's an application of something found in Euclid's Elements. Well, here it is, a one-page proof, and Cletus had an interesting question about how this step comes about, so let's break this down one step at a time. Here we go. First, this is the idea that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the sides. And we're going to use this diagram a lot, so I'm going to pin this. I'm going to keep referring back to this diagram here. Okay, so on this triangle, describe these squares. So they've made the red square and the black square and this sort of blue-yellow square. And we're going to try and show that this huge blue-yellow square, which is the side C squared, the hypotenuse squared, is equal to the sum of the black square and the red square. So let's see if we can do that. Now first it mentions drawing some of these things, so I'm going to switch my mode here. Draw these lines, the dashed black line parallel to the dashed red line. So that's what they've got right in here. So they're going and making this altitude to this side of the hypotenuse. So let's denote that with our parallel symbols. They're parallel, these lines are parallel. And also note that the black line, there's another pair of parallel lines here. The solid black line is parallel to this other line. Now it's hard to make that out, but what we're eventually going to use is basically this idea, that these lines are parallel. Okay? And that comes from the fact that we've built off 90-degree angles off of this corner and this corner, and 90-degree angles off of these two. Okay? Now, next idea is, since these angles are the same, because they're both right angles, when we add this little wedge in, we'll get these huge angles the same. So we get this angle like this is congruent to the angle like this. Those angles are congruent. That then sets up, went the wrong way. Now, what two sides are equal? Well, the dashed blue side is equal to the solid blue side. And what we're going to try and prove is that these overlapping triangles like this overlapping triangle and this overlapping triangle are the same. Let me emphasize that with another color here. We've got this big overlapping triangle like this, congruent to the other overlapping triangle like this. Those are the overlapping triangles we're trying to show congruent. We've already got a pair of angles congruent, and now we've got the blue side congruent to the dashed blue side, the blue side congruent to the dashed blue side. And here's the other pair. This red side congruent to the dashed red side. This side is congruent to this dashed red side because we set up as a square. So by what we call side angle side congruency, those two triangles are congruent, and that's what leads to our next step. We get those two triangles congruent. Okay? Now those two triangles are congruent. Now because of these parallel lines, you can say that the red square equals twice this triangle. How is that? Well, these parallel lines are set up so that you see that you're picking a point on this side so that the square and the triangle share a common height. And remember, for a triangle, its area equals 1/2 base times height, and the square is base times height. And the parallel gives you the impression then that the height of the triangle is always going to match the height of the square. So that's why the square is twice that triangle. I hope that helps, Cletus. Let me know if it doesn't. You see the same thing with the blue rectangle. And that comes from the fact that this triangle now, this yellow triangle, is half the area of this rectangle. Again, because of 1/2 base times height, and that the yellow triangle and the blue rectangle share a common height, like this. Okay, so that's why if they're twice, the red square and the blue rectangle are twice the same areas of the same triangle, and the same triangles are congruent, they have the same area, therefore the red square has the same area as the blue rectangle. Now, in the same manner, it may follow that the black square equals the yellow rectangle. And so I redid the diagram doing overlapping triangles in this direction, where I kind of tried to white out the old ones. And here's the new ones, and that is basically, this is a right angle again, in here, right angle here, right angle here. We add this common angle on, so we get this angle is congruent to this angle. So now to get the green and the purple triangles congruent, we've got these pair of sides congruent, because they're both sides of the same black square. And these sides are both sides of the same blue-yellow square. So those triangles are congruent. And as a result then, this green triangle is half the area of the yellow rectangle. And the purple triangle is half the area of the black square, because we can look at this as the same height, having the same height as the square. So that gets the square is equal to the area of the rectangle. As a result then, the square plus the black square plus the red square equals the sum of those two rectangles, and that's your basically a squared plus b squared equals c squared. And the proof of the Pythagorean theorem. Okay, yeah, there's Euclid's Elements of Euclid there. That's the original source, and this guy seems to have put together a nice colored diagram just in one page.